Hi all. Today we see a video about a paper called Optimal Model Management for Multi-Fidelity Monte Carlo Estimations, written by Benjamin, Karen Wilcox, and Max Wunsberger. So, what this paper is about? This paper is about to accelerate the estimation of the statistics of outputs of computationally expensive high-fidelity models utilizing a rich variety of multi-fidelity surrogate models. So let's see what this paper says about. So this paper says about there are a rich variety of multi-fidelity techniques like multi grid method for solving a system of equations, multi-scale methods, and also a multi-level Monte Carlo method for estimating stochastic partial differential equations with stochastic parameters and estimating the desired quantity of interest. So here, in all these multi-level Monte Carlo techniques, usually high fidelity model would be fine grid discretizations, and in particular multi-level Monte Carlo method, these low fidelity levels are from a hierarchy of coarse discretizations. So where the mesh parameter is adjusted to extract a different level of fidelity models with a known error and computational cost. So these models are usually utilized based on a trade-off between a error and a computational cost. So when we have a desired level of discretizations, the objective is to distribute the computational work among these discretized models, where shifting most of the works to the low fidelity models, and to occasionally use a few high expensive high fidelity models to establish a accuracy guaranteed on the overall result. But to exploit available more heterogeneous set of surrogate models, including projection based reduced models, data fit regression models, and machine learning techniques, possibly today are deep learning techniques, and also simplified physics models like simplifications coming from the uh, non-linearity or boundary conditions, etc. So how to exploit this rich variety of heterogeneous set of surrogate models in a multi-level Monte Carlo framework to estimate the quantity of interest. At the same time, it estimates unbiased estimator. So this requires rich variety of surrogate models with known and cost rates. So here, multi-fidelity framework is being presented, which try to exploit a rich variety of low-fidelity surrogate models of any types for acceleration of the Monte Carlo estimations of the statistical outputs of typically a large-scale, high-fidelity models coming from the partial differential equations. Here, the paper presents an optimization problems which find a solution to distribute the computational work among those selected multi-fidelity models in order to compute the desired quantity of interest such that the mean square error of the multi-fidelity estimator is minimized for given computational budgets. The solutions coming from the computation problem is claimed to be a unique and analytical solutions, and it can be also be applicable not only for the surrogate model has to have certain models, it also can, the information coming beyond those models can also be used as a multi-fidelity techniques, provided it has a known fidelity and a certain cost to extract those informations. This work been prior to this work, there are certain two-stage Monte Carlo techniques have been utilized to estimate the quantity of interest, often based on the control variate techniques. Here, estimator with the low variance than the Monte Carlo estimator is obtained by combining samples drawn from the output random variable of interest coming from both the surrogate and the fine fidelity models. For example, in multi-level Monte Carlo technique, cost realization approximations can be used, and also there are other techniques in papers has been utilized where reduced basis model has been used. But general surrogate model can be utilized in a control variate framework in order to obtain less mean square error for a quick start computational budget without affecting the biasness. So here the general framework is to make a multi-fidelity estimator using control variate method and balancing this number of model evaluations between the high fidelity model and single model. Not only a single model, but many different types of models can be more beneficial, such that the mean square estimator is minimized for a given computational budget. So this can be obtained by arbitrarily choosing any number of surrogate models, and moreover to again say that it depends on how that information is coming from the other from each surrogate models, giving the mean square error less compared to the high fidelity Monte Carlo estimations. To be noted, this MFA estimator to be proved that this is an unbiased. The reason is there has a reasonable occasional recourse to the high fidelity model. So this unbiasedness is independent of the quality of the surrogate models that we will be describing in the third sections. So now this second section is describing about the problem setup. Here we have an input domain of d dimensions, and the output quantity of interest is scalar output, and there are different variety of computational models are chosen, and it has been hierarchically ordered from F1 to Fk. F1 is a high fidelity model, F2 to Fk are low fidelity models, and each F2 to Fk have a computational budget from W1 to Wk. And one particular important thing is there is not any necessity to have some point wise error criteria like I mentioned in 2.1 to be included for the multi-fidelity framework. So the variance of the Fi model is defined by equation 2.2, and the correlation coefficients between the two models like I and J is defined by equation 2.3, as we know. So if we here the main theme is here we typically ignore uncorrelated model to the high fidelity models. We only choose a model which are having a correlation coefficients greater than 0. So the Monte Carlo estimator, as we know, is given by the equation 2.4 for any model I. And we also know that the estimated 2.4 estimate is an unbiased estimator, and the mean square error is given by this equation, which depends upon the variance of Fi and the number of samples chosen. And the computational budget is for each computation budget defined as Wi, that the number of samples multiplied by gives a total computation budget. And the problem formulation is like if we having a high fidelity Monte Carlo estimator by 2.5. For that budget, we wanted to try to build a multi-fidelity framework such way that the mean square error is much lesser than the mean square error computed by equation 2.5. So for this, we choose a different variety of multi-fidelity models like F2 to Fk, and we utilize them for a fixed computational budget. So this is derivations like how these multi-fidelity models are the given multi-fidelity models, how those models are chosen, and then how many samples are chosen from each models from through an optimization problems which distributes the model evaluations among the high fidelity models and the selected surrogate models, provided there be a correlation strength between the high fidelity and the low fidelity models and the relative computational cost. And also it is proved that MFZ estimation is an again unbiased estimator. So we have chosen number of samples from each one to be C1 to CMK, and and the models are evaluated for the chosen number of evaluation for the each surrogate models. And from by those given informations, we estimate the MFFA estimations that which replace the equation 2.4 to be from the equation 3.2. It is something like that. It uses a M1 high fidelity model, not like M is very large compared to M1. And this is like iterate summation through that low fidelity model from 2 to K. So here the objective is to choose what models has to be improvised in this estimate, and also choose the alpha 2 to alpha k, and also m1 to mk. This is the objective of the optimization problem. And it is we see that the equation 3 point is similar to the multi-level Monte Carlo estimator given in this reference 15 to 40, 46. And one difference is it uses the rich varieties of the low fidelity models, and the alpha to alpha k is and m1 to mk is chosen from the optimization problem. And again, similar to multi-level Monte Carlo, MFMC is an unbiased estimator, and the mean square error of this is given by in the equation as mentioned earlier, that variance of s, and the total computation budget is here. Then now here we see that lemma 3 says that the covariance, this helps us to make the variance estimator to be as this one, which depends upon the number of samples in each and every fidelity model, and their corresponding variance and their correlations with the high fidelity model. So this objective is taken, this variance is taken as an objective to formulate an optimization problem to determine alpha 2 to alpha k, such way that that mean square error, like the variance defined, is minimized. And the formulated optimization problem is this one 3.10, that the variance what we have defined here in equation 3.2 is the variance of the MFNC estimator is try to be minimized depending upon the variables of the number of samples from each fidelity model from M1 to MK. At the same time, also the correlation, the alpha variable that appearing in the second term is also to be chosen as the variable that has to be identified by minimizing problem with subject to this constraints. And based on that obtained thing, one of the thing is that there will be hierarchical correlations from model 2 to 2k. And once we solve that, this is the estimation we obtain for the alpha 2 to alpha k and m1 to and mk. So ultimately, we have identified those explicit equations for alpha 2 to alpha k and m1 to mk, which gives you a local minimum for the fixed computational budget for the MFMC estimation, which is again we emphasize that it's an unbiased estimator. So one of the important criteria is that this equation 3.2 has to be satisfied to in order to obtain that optimization problem results, which says that something that this there should be some kind of a correlation between these successive models between I and I plus 1 model, and also that budget computational budget is such a way that arranged such a way that when we are putting this equation, that has to be less than 1. So it not only depends upon the individual models, it also depends upon the group, how the models are being set, so that hierarchical workload and hierarchical correlation has to be established. So these correlation coefficients lead to small terms in the equation 3.23, not only the individual things, and also how the computation budget is arranged from 2 to 2k. So the contribution of model Fi to the variance reduction is high if cost W are low and the difference of the correlation coefficients between Ri and R1 is low. That's what this from the contributions from this says about that. So it is clearly saying that considering only the properties of the model itself is not required, but requires taking the properties of other things used in the MRC estimator into account. So this estimation is computationally cheaper than the Monte Carlo estimator is not the condition on the properties of the each model separately, but rather is a condition on the properties of all the models from F2 and 2 together. That is a whole collection of relations between those models plays a key role in estimating the MFFC estimates. So 3.4 gives some illustration which we don't go further things. We are mainly targeted in this video is to describe and to understand the MFMC techniques. So how these models are selected, and how among the different model, how which are the models to be selected is defined based on algorithm 1. The algorithm 1 is something like defined in this one, which possibly in later please go through this paper and see this has been explicitly coded in the MATLAB code. And from this what they says is they will be iterating on a different combinations, and there will be different combinations iterates over all the subsets among these ones, and finally a particular subset which gives you a best estimate for that particular budget will be chosen. And once that particular subset optimal subset is chosen, then we are in a position to estimate alpha to alpha k amount to mk, which we need a sample variances and sample correlations from the identified from the few samples are initially computed, and those are given as an input to this algorithm 2. And finally this algorithm 2 estimates how many samples to be computed from m1 to mk, and that alpha to alpha k, that would be the output from the algorithm 2. So once we have these things, and it would be easy for us to compute the MFMC estimates drawn from different how many samples has to be drawn from each surrogate model that would be drawn. And one we know the alpha to alpha k, we put it into that equations of MFC estimate, and finally we compute the desired quantity of statistics of the quantity of interest. So numerical estimates is beautifully written here, which will try to avoid this to have to make the videos within stipulated time. But this might be given as a separate video which is beautifully and the results are produced in a crystal clear way. So these are the results. The graphs are very beautifully done. and and finally in the conclusion is, yeah, this paper leverages computational chief of arbitrary surrogate models to reduce the running time of the estimates of the statistics of the expensive high fidelity models. And also it definitely maintains unbiasedness of the resulting estimator. And that it also says that there are many varieties of models can be utilized, and it gives you a several, and through the results it shows that the speed up is several orders of magnitude compared to the high fidelity estimator. So the again it says that the estimator is unbiased, independent of the availability of the prior error bounds on posterior estimates of the surrogate models. But this paper has only proved for the scalar quantity of interest, but in the future they have a plan to give for the vector quantity of interest. One ad hoc way would be to compute each element in the vector to be as a scalar quantity of interest, and try to estimate this and bring about the setup the setup he has given for this one into a vector value setup. But a deep extensions will be done in the future work. That's what this paper says about. Okay, thank you.